Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. The p-value or p-valued method is particularly important in business statistics for three different reasons. One reason is that virtually all computer software statistical packages yield a p-value as an output. So we all have p-values when we analyze data in the computer. Another reason is the p-value method is very popular with business statisticians, and so it's important that we understand their methodology. And a third reason why the p-value method is very important is that we are able to reach a conclusion in hypothesis testing without determining critical table values. So what is a p-value? Well, another name for a p-value is the observed significance level. The p part of the p-value stands for probability. So we might ask, a p-value is the probability of what? Let's consider our observed z that we solved for in a previous example. What would be the p-value of this particular observed z? Let's draw a graph. In the graph we have a mean z of 0. And what's happened with this observed z, with a 2.22 observed z, it falls quite a ways over to the right of the distribution. And what we do in the p-value method is to determine how far out towards the tail does it actually fall. As a matter of fact, we will discover that the p-value is actually the portion or proportion of the curve that is past the observed statistic. So how do we go about finding this so that we can determine if this falls in the rejection region or not? Let's take our observed z value of 2.22 and go to the standard normal z distribution table and find out what area is associated with it. When we look this value up in our table, we find an area of 0.4868 associated with it. In our graph, the 0.4868 is the portion of area between the mean and where the z value falls on the chart, or the inside part, if you will. Understanding that the normal curve is perfectly symmetrical and that 0.5000 of the area is on each side of the mean, we can subtract our 0.4868 from 0.5 and get a result of 0.0132. 0.0132 then is the area under the normal curve that's past the z value, or the tail of the distribution past the z of 2.22. So 0.0132 of the area falls here. This 0.0132 then is our p-value, and it's the portion of the graph that's past the z value, in this case 2.22. It's the portion of the graph that's in the tail of the distribution. So our p-value is 0.0132 in this particular distribution. What does that really mean? It means that a z of 2.22 is so large that only 1.32% of the values would randomly occur past it. Or in other words, only 0.0132 of the time would you randomly have a z value occur greater than 2.22. So now let's talk about making a hypothesis testing decision using a p-value. Let's return to our z equal 2.22 and see how we would arrive at a hypothesis testing decision. So our observed z value from a previous study was z equal 2.22, resulting in a p-value of 0.0132. Suppose alpha was 0.05 for this one-tailed problem. How would we make a decision about the null hypothesis using a p-value of 0.0132? Well, alpha, as you know, drives the size, is the size of the rejection region and drives the location of the critical value. So let's draw that in. If alpha is 0.05, then the critical value is going to be back here so that we can have 5% of the area past the critical value. So therefore the rejection region lies to the right of this particular line. Notice that our p-value, though, is past this, deeper in the rejection region. Because our p-value falls out deeper in the rejection region, our decision would be to reject the null hypothesis. That is, in this particular case, because our p-value in a one-tailed test is smaller than alpha, we reject the null hypothesis. Suppose, on the other hand, we were using an alpha value of 0.01. What would our decision be now with our p-value of 0.0132? Well, let's draw our normal curve again. And we still have an observed z-value of 2.22 with a corresponding p-value of 0.0132. But where is the rejection region based on this value of alpha? Well, since alpha is 0.01, and that determines the rejection region and where the critical value is, we can see that 0.01 is less than our p-value. And so 0.01 is actually going to fall further out than where our p-value lies. That is, we will have an alpha of 0.01 further out in the tail. Our p-value will be back to the left of the critical value that's produced by alpha. So therefore, if alpha is 0.01 on this one-tail test, our decision is to fail to reject the null hypothesis because our p-value is greater than alpha. A conclusion can be reached about p-values from seeing these two examples and from other information that we have. We can say that a p-value defines the smallest value of alpha for which the null hypothesis can be rejected. It is the smallest value of alpha for which the null hypothesis can be rejected. So in this particular problem, the smallest value of alpha for which we could reject the null hypothesis is an alpha of 0.0132. Now the problem with that is, as you probably know, the common values of alpha that we study and we use are alpha equal 0.10, alpha equal 0.05, alpha equal 0.01, alpha equal 0.001, and alpha equal 0.0001, and so on. We don't have an alpha of 0.0132. If a p-value is the smallest value of alpha for which we can reject a null hypothesis, then you can see that we are, in this particular problem, unable to reject the null hypothesis for alpha 0.01 or less, because 0.0132 is bigger than 0.01. But we would be able to reject the null hypothesis for alpha values of 0.10 and 0.05. As another example, let's consider what the p-value would be for an observed z of 1.45. If we look up a z-value of 1.45 in the table, the area associated with it is 0.4265. And let's draw a graph. We have an observed z of 1.45. The question is, where does it fall? Well, the 4265 from the table is this part over here. If we subtract from 0.5, we get the p-value, which is 0.0735. So our p-value for this z of 1.45 is 0.0735. Would we reject a null hypothesis based on this particular p-value? Well, from what we learned before, this p-value is the smallest alpha for which we can reject a null hypothesis. Nobody has an alpha value of 0.0735, so the smallest common value of alpha that we use for which we could reject a null hypothesis is an alpha of 0.10. So we can conclude if alpha is 0.10 that we would reject the null hypothesis. If alpha is 0.05 or less, we would fail to reject the null hypothesis because the p-value is bigger than this particular alpha. So for alpha values 0.05 or less, we would fail to reject the null hypothesis. So now let's summarize about p-values. Another name for the p-value is the observed significance level. And what that means is the p-value tells us exactly where on the distribution the statistic falls. Because we know exactly where our observed z or t or chi-square falls in the distribution, there's no need to have a predetermined value of alpha. And there's also no need to have a critical value or a table value against which to compare the observed z or t. Also, because we do not have a predetermined value of alpha, we can use the rule that the p-value is the smallest value of alpha for which the null hypothesis can be rejected in order to make a decision.